Thank you for attending this talk. I am associate professor at the University of Juan Carlos, where I teach functional programming with Scala. I'm also co-founder of Aula Computing, which is a small consultancy. We specialize on data engineering with Spark and KDB plus Q, and we have been programming with Scala for the last 13 years. I also manage the Scala Meetup group in Madrid, and I'm also member of the program committee of Lambda World. We have been playing, as I said, with the Scala and particularly with functional programming for a long time now, with tagless-final in particular. And the purpose of this talk is talking about tagless-final, mostly from an architectural perspective. We will spend some time talking about what is tagless-final and how to apply tagless-final in a step-by-step fashion. But the major takeaways of this talk are intended to be related to the advantages and disadvantages of tagless-final functional architectures in general. Let's start. Okay, so first of all, what is a functional architecture? Because, okay, when we talk about functional programming, we talk about higher data types, higher order functions, type classes, and other modularity techniques. But as Phil Walder says, functional language is a domain-specific language to create other domain-specific language. And this offers an architectural perspective whereby the architecture of a functional application can be understood as a stack of DSLs, of purely declarative programs, which are compiled or interpreted into each other until eventually side effects are raised. Okay? So let's see a particular example. Let's say that we want to extract some information from the commits of a GitHub repository. Let's say the name, the email, or the login and the creation date from different commits. Okay. In order to do that, we can use the GitHub API and access this paginated endpoint. So that our application, and this paginated endpoint will return an array of different commits for each page. Okay. So conceptually, we can design this application, this small application, as a streaming application with two major stages. First, we generate all pages, all the arrays from the different accesses to the endpoint, the GitHub endpoint. And then we essentially will flatten these arrays and we'll extract the relevant information from each object of the arrays, okay, from each commit, right? So how do we implement this? Okay, one alternative is to use SEO streaming. To be honest, this was the first time I was using SEO, and it was a really nice experience. It was really easy to implement this small application. For the generation of the stream of pages, we just implement with SEO HTTP a small method in order to get a small function in order to get the JSON array, and then we will constantly repeat invocations to this endpoint with increasing page numbers until eventually we obtain an empty array. Okay. For the second stage, it's also really easy. We start from a string of arrays, so we flatten these arrays and then extract from each commit the relevant information, and we encapsulate this author login and commit message fields in a small array, right? So the architecture of this small application fits the picture that we saw before. We have SEO strings and SEO JSON programs at the top level, which builds upon CO HTTP program, and both of them builds upon the CO core, right? Now, this program is fairly abstract, and it is implemented using high-level abstractions and higher-order functions like mag and so forth. Okay, but for instance, we can do much better in terms of the clarity of our program using just the JSON query language. Using JSON JQ, okay, we can implement our string transformation in this very simple way. First, we iterate over the commits of the arrays, and then for each of these commits, we extract the author date and the author log information and collect all this into an array. So this is really nice, but we love to be in the Java ecosystem. We love to be in the CO ecosystem. And why not to implement our string transformation in this way? Let's say that what we want actually is to implement CO pipeline, okay, the string transformation using CO string, but using the abstractions of JQ. So what we have to do is to embed the JQ language in Scala and give a CO interpretation, right? How can we do this? Well, there are different alternatives in order to embed a DSL in Scala. One of them is the tagless-final style, right? This is an approach that was put forward by Oleg Kishelyov and colleagues. So how do we apply tagless-final in order to embed the DSL? Well, what we propose is to follow a number of a step-by-step method. Okay, and in the first one, what we are going to do is to work with a fixed domain, with a fixed semantics domain. What we do is to start from sample programs, like the one that we show, okay, and write just the syntax that we need in order to implement these programs for this particular semantics. So in JQ, all things are filters, string transformers, okay? And so our filters in this particular case, for this particular semantics, and in this first step is just a CO pipeline, right? And the syntax that we need in order to write this program, well, we need an iterator, we need a pipe combinator, we need an array combinator, and then we need this string interpolator or filter interpolator, right? Syntax in the tagless-final style is not implemented in terms of data types. It is just implemented in terms of functions, in terms of semantic functions, right? In this first step, we also can implement, of course, all these combinators and these primitive filters. For instance, the iterator filter can be implemented in terms of map and flatten, right? But in this first step, we can also take into account the difference between the surface syntax and the deep syntax in our language. So for instance, in JQ, this expression actually is a syntactic sugar is written using a lot of syntactic sugar. First, this is written in terms of pipe, and then eventually what we have is that this expression builds upon the identity filter, the string constant filters. These are primitive filters and combinators. Similarly, when we write this expression, this comma refers to the concatenation filter. It is not a syntactic element of a comma-separated array. No, it is the concatenation filter. And also, what we can take into account in this step is the built-in library. In JQ, there are lots of filters which are written, which are implemented in terms of more primitive filters and combinators. So the end result of this step is something like this. What we have is an implementation which is structured around the different primitives, around the combinations and filters that refer to the syntactic sugar and built-in function, okay, the built-in library. Now, let's say that we want to do this, but not for the CEO pipe, the CEO ecosystem, but for ACK. What we will have to do is essentially the same, but for the type of our filters and the implementation of the primitive filters and combinators of the deep syntax. And if we want to do this for the FS2 library, FS2 streaming library, similarly, we can reuse a lot of things, but and we only had to change the type of the filter, which in this case would be a pipe, and then to implement again all the primitives. Okay, so we can do this, of course, with copy paste, but this is no good. So in our next step, what we could do is to abstract from the fixed particular semantic domain and define the class of JQ filters. We can use a type class, right? And these JQ filters are semantic representations, okay? This trait is parameterized with the possible types that can play the role of a JQ filter that we abbreviate with R, right? And in this trait, in this type class, all the primitives of the deep syntax are abstract, right? And the other syntactic sugar and built-in functions, we can get them for free, right? The syntax is normally implemented in a separate module, okay? And then what we need to do is to implement the semantics for CO streams as a given instance of this type class. And with all this, we can already implement the very same program that we implemented before. If we want to implement the program for SIO, then we can import implicit instances from for SIO and so forth. Of course, what we can do also now is to implement our program once and for all for any particular semantics, right? With an ad hoc polymorphic method. And in Scala 3, we can also implement this using polymorphic function types, right? Well, this is nice, but this is not necessary at all, okay? But we can already do it. No, so let's start, let's move forward, and now let's deal with types. JQ is a dynamically typed language, which means that we can find type errors at runtime. For instance, in this small program, this program basically what it does is to iterate over the JSON elements of the arrays that we will find in the input string, if in the input or objects, okay? We can iterate also over the members of objects. If in the input string we do not find an array or an object, okay, there will be an error. And this error will be a type error. We also have in JQ try catch and error primitives. And so taking into account this information, we can update our API for our language and include, for instance, the different error types that we can get and these new combinators, right? Now, taking into account this information, of course, we had to update our semantics, and the CO pipeline we won't return a string of JSONs, but a string of either JSONs or errors. Okay, and for this feature, union types are really, really nice, right? And we can complete the implementation of our primitives. Okay. Now, there is a big difference between these two programs that we have here. This program may fail at runtime. We can't do anything about it, okay? But what about this program? This program, what it's doing, this is the string constant filter. And this filter will always generate a string of high, 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 high. These JSON strings are piped into an iterator, but the iterator requires demands, arrays, or objects. So we can say at compile time that this program will fail, will always fail at runtime. So what we would like is to reject this program at compile time, right? In order to do that, what we need is static typing. What we need is a type system, right? And in order to implement this type system, a type system is simply a set of typing rules which allow us to assign types to our programs. Okay? And the types for our programs will just be filters. Filters which are parameterized with the type of the JSON elements in the input string and with the types of the JSON elements in the output stream. So high is a filter with no matter which kinds of JSON elements we find in the input string will generate strings. The iterator demands a JSON array or object, okay? This is a simplification. And the pipe combinator will create a new string transformer provided that the first and second filter, the output of the first filter matches the input of the second filter. And well, how do we implement this type system? The first thing to do is simply to implement the type of our types, okay, for the type system. And we do this very simply with a filter trait, which is parameterized with the input and output types, with a JSON algebraic data type to implement different JSON elements. Okay, and notice two things. First of all, these filters are contravariant in the first argument and covariant in the second argument, and this is very much like function types. Okay, and really important, these filter types are sealed. The filter types are sealed, which means that we do not care about the instantiation of these filters. These filter types will be used only for the sake of the implementation of the type system. They will behave as phantom types. Now, concerning the typing rules. The typing rules will be implemented by extending the type class, the JQ type class. And what we will do is first, instead of being parameterized with a simple type, we will use a type constructor, right? And the purpose of this type constructor and the parameter of this type constructor is to annotate the type of the expressions of the program that we are reading. What we have to do is simply to annotate, okay, for each member of our syntax, okay, we have to annotate, for example, for the iterator, we have to annotate which kind of filter we are creating, right? And this has a one-to-one correspondence with the type level, with the type system that we saw before more formally, right? And with all this, we can, whenever we write this method, it will be rejected at compile time, okay? And the Scala compiler will return this kind of message, right? Now, of course, what we have to do as well is to update the instance of our type class, okay? Because we now have a type constructor, but this is fairly easy because we can just ignore this filter type that we use in the type system and return the CO pipeline that we used before. And what we have here is a kind of type erasure, okay? Because we are forgetting about the type information from our programs. So, which are the advantages of this methodology, okay? First of all is simplicity. We can start just with implementation of our DSL, of our embedding, just for a particular domain. Okay, this is fine, right? It is not necessary to define a type class to abstract away from particular semantic domains, or even implement a static type system. Okay. Of course, implementing a JQ type class and abstract for particular domains can provide us a lot of reuse. Okay, we can reuse a lot of things. We can reuse the standard syntax. We can reuse the standard semantics implemented in terms of lazy lists or iterators. Okay, we can reuse testing facilities and so forth. We already did this for the JQ embedding. Okay, you can find in these GitHub repositories of the JQ Scala organization the implementation of this presentation. So in conclusion, always look on the declarative side of programming. Okay, there are always chances to write in a more declarative style. There are always chances to implement domain-specific languages for your application domain. There are many advantages in order to be more declarative. Also, tagless-final is all about implementing DSLs, right? This JQ type class here is unlike the monad type class in many ways. Okay, the monad type class is a class of computations or data structures. This JQ type class and tagless-final type classes are classes of semantic domains. In this case, are the classes of JQ filters. Okay, and when we use a type constructor class, and because we are implementing a type system, this parameter here represents the types that are assigned by the type system, right? It is not about the output of some computation or the type of elements of some data structure and so forth. Also, keep in mind this principle, okay? Maybe it is not needed to implement the type class abstract from particular semantic domains. Maybe it is not necessary, okay, to implement the type system. This will add some complexity to your code. There are some times in which it is not needed. In the particular case of the JQ embedding, I think that it would be really nice. In the Scala ecosystem right now, we have different frameworks. We have the CO frameworks, we have the ECA frameworks, we have the type level frameworks, okay? And these behave very much in like closed ecosystems, okay? And I think that much can be gained by having not a JQ DSL that is defined for any particular implementation, but also why not a streaming DSL, a JSON DSL, an HTTP DSL, for instance, Tapir. I think that it goes in that line, and this is really nice. Okay, and this the overall goal of this is fostering competition and avoiding vendor locking, which I think that it is really nice, and I think that the tagless-final style can be really good for this matter, right? So some references. Contributions are welcome if you want to join this effort of for implementing this JQ embedding. You are more than welcome. This is just a proof of concept. Okay. The source for the tagless-final style is, of course, the FTP site of Oleg Kiselyov, but you can also have this tutorial in our GitHub repository that I think that it is quite good in order to illustrate this difference between monadic and applicative applications and the tagless-final style, which are quite different. Okay. There are other approaches, okay? Not only tagless-final. I think that the important thing is the DSL architecture for functional programming. Right, that's all. I hope to see you around Madrid or Cádiz, Atlanta World next year. Thank you very much.